could do pretty good exercise. You throwing those out there.
Or I could just we can just stare. I'll be in the back. You guys got me.
Good morning, everyone. We're Team Pink, and here's our prototype, SmartLine.
Okay, first we're going to do some introductions. My name is Daisy, and I'm from Denver, Colorado.
All right, hi everybody. My name is Stella Bubbins Hill, and I come from Delta, Colorado.
Hi, I'm Maz, and I come from Aurora, Colorado.
I'm Jose, and I come from Greeley.
I'm Trenton Frankenfield, and I'm from Lone Tree, Colorado.
Okay, so a little bit of background. Each team was tasked with inventing a prototype or improving some device in order to make the efficiency of mine rescues better. So mine rescue teams usually have about 6 people who all have their separate jobs. For our prototype, we're fixing a problem with the map person to improve communication between the underground team and the fresh air base. The map person is basically the leader, and he has to navigate everywhere. They have to relay the information to the fresh air base and then track where they are and any difficulties with the terrain. Some challenges with this is they have a hard line, and that can get tangled, especially when you're turning back and forth because a path is blocked, or there might be poor conditions with lighting and water.
Okay, so our problem statement was, how might we develop a more efficient communication system between the map person and the fresh air base that balances convenience and reliability?
All right, so once we established our problem statement and decided what we actually wanted to focus on, we initially started with individual brainstorming, and then we moved on to a team collaborative effort where we finally decided on 2 main areas we wanted to combine and focus on. So first, we wanted to develop some kind of an automatic tethering system for the hardline communications, which would make it easier for the mine rescue teams to deploy the hardline and not have difficulties when actually traveling through and navigating the mine. Secondly, we also wanted to focus on developing a sectioning system where the miners could actually determine which areas of the mine had different areas of danger and what key items there were to know about.
So for the initial building, as you can see here, in here we have a battery with an Arduino, and we have a display. This will show how far people go, and it'll efficiently track the distance so that they could relay it back to the map person.
Oh, and this is our piece that we 3D modeled. It's very simple. The way it works is we just needed something that connected the motor to the actual tube to make it spin. It didn't come out perfect. We had to do some drilling, some filing, and some sanding, but it came out pretty good.
All right, now we're just going to do a brief demonstration of how our system actually works. So again, this is the communications box that the mine rescue team is going to take in and the map person is going to have. These buttons represent different danger symbols in the mine, and they can actually use them to communicate with the fresh air base.
Okay, and as the team walks, their hardline will slowly be reeled in back again by this motor here, so that if they need to turn around, the hardline won't tangle with each other.
It makes the communication system much easier to work with when actually on the field.
And of course, this is just a prototype. So basically what this does is it's going to retract the hardline communication system back towards the base of the mine. So again, the mine rescue team doesn't have to continuously deal with the hardline, and it makes it much more efficient.
There we go.
So here's our reflection. This project gave us an opportunity to learn a lot about mining rescue operations and also the challenges rescue teams faced in the mine. So through tours and research, we were able to learn more about the key elements of communication used by mine rescue teams. And if we were given more time as well as better materials like a stronger motor, we would definitely flesh out this prototype way more and develop a system for mine rescue teams to deploy hardline communications efficiently.
And these are our sources. Can't really see them, but.
Thank you.
questions?
Any questions for this group? Or have a mic. Any questions?
You in the back.
What was a big issue that you guys ran into and how did you overcome it?
So we actually had a problem with the motor. So we used a first motor, but it wasn't strong enough. The thing was this pipe weighed so much, and then there was a lot of friction on these like turning parts here. So we had to find a new motor, a stronger one with more power to actually get it to turn. And even now it still turns kind of slowly. So like I said, if we had a better motor, we could push out this prototype more.
And then
If you guys would like get all the materials and the time to do so, how long do you think it would take to build like a final product?
I want to say give us another week, and for sure we have another fully functional prototype.
Yeah, I think the design process ultimately includes a lot of different steps. It's constantly making new prototypes and then being able to refine them and learn from what we've already developed and then like make new progress with that. So I think it would ultimately be a process where we're continually learning as we make new designing developments. Yes?
What was some new stuff you did doing the project?
I could take this one. So I never really had any experience with like circuitry or coding. So, and I designed the display feature. So I think I learned a lot about like, oh, how code works and how that works with circuits in Arduino.
Any more questions from anybody?
So is each person problem or is it just like one and then everybody has a product?
Oh, I can take this.
So,
one. All right.
okay, sorry. So because the map person is the primary base of communication between the underground rescue team and then the fresh air base, we would ultimately have the map person carrying this communication box. And then because it also has buttons for the different types of hazards that they encounter in the mine, that allows the map person to record different dangers and hazards that they encounter and then instantly communicate those back to the service team.
What advantage does this have in comparison to wireless systems that has the similar functions?
So with wireless systems, they're nice, but they're also unreliable, especially in different parts of the mine. That's one problem with the current like radio system, is that they might cut out or lose frequency, which is why the hardline makes it easier and why a lot of traditional teams use that. But then the hardline also has its challenges with getting tangled. And then another benefit is also traditionally miners would use 2D maps and draw the changes. But if you're in water or have bad lighting, it's really hard, which is why pressing a button and then just sending it automatically makes it a lot easier.
Any more questions? Awesome. Let's give them a round of applause. Before you guys settle down, we're going to take a quick team photo. If you guys want to hold up your prototype if you guys want, or have it out in front. You guys can also put the hard hat on if you guys want. We don't have to.
All right, we're fine.
Great job, guys. So we're just going to go to our next group, which is Team Blue. Team Blue is up next.
Is he just picking random?
Hi everyone, thank you for coming today. We're Team Blue. I'm Sumant Kaja.
I'm Paula Garcia. I'm Izzy Pennington.
I'm Mustafa.
And I'm Christopher Koo.
And our project was called the SABRE, which stands for Subterranean Atmospheric Biohazard Evaluation Rover. So our problem statement goes as follows. How might we optimize operational efficiency and safety during gas detection procedures across diverse environments? This problem occurs when we look at specifically mine rescues, when we have the team of people rescuing people that get stuck in mines. We decided to look into the role of gas person, whose job is to map dangerous parts of the mines, specifically hazardous gases that have issues with flammability. This is a crucial role in the system of mine rescues, and that's why we decided to make it more efficient with this saber.
So for some of the current issues that a lot of the miners face, in most mines, there usually is methane, carbon monoxide, hydrogen sulfide, nitrogen dioxide, and ammonia, which is not visible to the human eye in most cases. So most individual miners usually carry an MX6 with them, which kind of just lets them know what type of gas it is. But before this process, usually a gas person puts some type of gas detector on a probe, and they go around the mine, and they kind of just scan it and see where the gas is. Then they use this to determine whether it's safe to proceed or not. However, this process can usually take a lot of time, so it's very inefficient, and it's more risky for the actual gas person and the team as a whole.
So the solution we came up with was a remotely controlled robot that allows the gas person to not directly interact with the dangerous gases, which eliminates the danger levels of the rescue. What we have are two examples of potential types of wheels that can address different types of diverse environments, because we don't know what kind of environments they can encounter, especially since there could be explosions or changes to what they were familiar with before. And one aspect we have is a pole where we have different sensors at different levels to address the problem of gas stratification, where different densities of gas reside on different levels. And since we have a pole of different heights, we can have multiple sensors that simultaneously detect the gases at the same time, which increases safety and efficiency. And we also can have the pole adjust heights to address the problem of different ceiling heights as you move along the cave or the mine. We also have a detachable pole. So in any case where the robot is not the most efficient option, you can remove the pole and just manually go back to manual detection.
For our prototype, we used Arduino for electronics as well as 9-volt batteries. But for our design, we decided to use lithium batteries, which would be housed in an explosion-proof case in order to prevent the risk of fire inside the mines. Alongside that, we were planning on adding a sensor so that we could not only map out the area in front of the miners, but also make sure that the robot doesn't run into any other obstacles that could cause damage.
Yeah, so here's our process. So first we learned about the different roles and functions of people in a mine rescue team. Then we went to the Edward mine and we toured it. We got to talk to the miners over there about questions we had, such as like the limitations and advantages of technology that they use for gas detection. We also asked them about like specific problems that they see in mine rescue operations. Then we did some brainstorming and ideas for solutions. As you can see here, we came up with ideas for all the different people in the team. We ultimately decided on doing the gas person. Then we made sketches of our design. We collected the materials, and then we started building the prototype. And that's what this is also ultimately what we came up with for the saber. Overall, it was a really fun experience for us, learning, designing, and building the process, the prototype. And it was a really fun experience for all of us, yeah. Thank you.
Awesome. Does anyone have any questions?
What exactly do you guys have for the wheels that would help to like bypass the like terrain problems, like grooves on the wheels or like specific sort of treads?
So these are just two examples we have. So depending on like, because each mine could vary, so like there could be different options. So we have two potential examples where we have treads, which allows it to like match the shape of the environment, or we can have wheels if there's like a bunch of like rugged rocks that you just need to traverse over.
How would you change the design to deal with like deep puddles of water?
We could make the tires or the treads extra inflatable. That way there is some distance above the ground, and we could add some waterproof casing as well.
Yeah.
Were you thinking that this robot would be autonomous, or would it be?
So we were thinking about both of them. We probably thought like it could be autonomous, but like the gas person could have like a camera to like see where it's going and like make sure it's going on track. It could like switch to manual or automatic depending on the circumstance.
Yeah, and also, we think that either way, it does help the gas person with the role because they have to scan all 3 or 4 sides of the mine when they're going through the mine rescue process. And that takes a lot of time, and then mapping it also takes an even longer time, which can risk the lives of a lot of people stuck in the mines or even risk the health of the people performing the mine rescue. So we think that with this robot, whether it's controlled by someone or it's autonomous, either way, it's saving a lot of time.
Yeah, it's very efficient and it like helps you get all the areas without having to spend more time on it.
Will the saber be relaying the information to the fresh air base, or will it be relaying the information to the group that's behind it?
We think that it would be relaying the information to the group behind it because the the gas person is already mapping. That's their current role today, and we want this robot or the saber to actively be changing or updating the map with the data that it receives.
Yeah, but that's a very good point because the gas person obviously has to do their own detection, and they may have to like control multiple robots potentially. So in that case, maybe the fresh air base could like control them from their vantage point, or like somebody else besides the gas person will do that.
How would you handle mapping gases at multiple elevations because of how different gases settle?
Yeah, so
we can have an extendable pole, so it's adjustable. Since like mines, like the height of the mines does vary, so we can have it also move around. And we also have multiple sensors on the pole to address the problem of gas stratification.
So it looks like it would be run remotely. Do you think that there would be a way for it to be autonomous in its travel, kind of like a Roomba, or could have free settings so it could go on its own so nobody would have to manually direct it?
Yes, we can do both. So we could have a setting where it could be controlled by remote control by, say, the gas person. But since we designed it to have a sensor on it, we can program it so that it can maneuver the mines by itself, which could also be useful for mapping multiple areas at once.
With the lithium batteries you guys were planning on using, how long do you think the robot would last for in line?
I need to do more research on that, honestly. But if we make it rechargeable, I think it could take up to a couple hours depending on what kind of battery we use, or if we use multiple batteries.
What was something new you learned this week that you used to make your prototype?
Definitely like Arduino, like the hardware of it and the software of it. Yeah, that was a new experience for I think most of us.
Yeah, I have like no prior experience with coding in circuits, so like seeing like Paul be able to do that and Mustafa be able to code and seeing those to be able to 3D print, I just learned a lot of like how multiple parts come to one whole. And it was really cool being able to work together since we all know different things and have different experience.
Yeah, no, it's going to be loads of pieces of manufactured with multiple of these, like for like an average mine, how many of these do you think would be running around?
I mean, it depends on how much they can like afford to spend on it. I don't think it would be super expensive because it's not like we're using any like kind of advanced technology or anything. It can just be kind of like a sense, like it just needs sensors, it needs the body, and it needs a retractable pole. And obviously, I think honestly, the like a big cost of it will be the detection device itself. But otherwise, I don't think it's like that big of a expense.
We also designed it so that the people in the mines can use the gas sensors that they already have. So we made it detachable, so we don't have to spend money on all the gas detectors, which make up a big cost.
Right.
You have time for one more question.
What would you say you guys are missing from a fully functional prototype?
I think definitely the voltage of the batteries was an issue that we already had to deal with, but yeah, the batteries and the motors just not being able to spin, I guess, as fast and as powerful as we wanted, made it so that we couldn't really have the robot move because of the weight that it was carrying.
Like they can spin a bit, but like not really.
It's just not getting enough amperage
not
because
enough.
of the type of battery and motors that we have.
Yeah. Okay. Thank you, everyone.
Thank you.
And then we'll try to get like the. Let's go, guys. All right, next up, we got team green.
Okay. My name is Diddy.
I'm Gabe.
I'm Sarah.
I'm Nico.
And our project was a carbon integrity system, CIS, which we will explain a little bit more. The problem that we were facing was how might we make the knowledge of the cave's composition and the structural integrity of the caves more accessible to the mining team through chemical experimentation and encoding it into an efficient technology. So basically what that means is how would we have the integrity of the mines accessible to the mining teams right before they enter the mine and rescue. So how to solve this was that we determined the composition of the walls of the cave and how stable they are through a chemical experimentation, and then we put it through a specific device measuring the gas and then putting the data into an Arduino.
How else? Okay, so from 2015 to 2021, there were quite a few large limestone mine collapses around the U.S. This was due to many purposes, mainly because the structural integrity of the walls wasn't as strong, and this killed people in the process as the mines collapsed in on them, and it also created sinkholes, wasting a ton of money and resources and tools that were lost. The following photos are some of the collapses in the past decade of limestone mines and the sinkholes they caused. Some of them, the air blast from the mine also blew people and equipment like 50 feet into the air. And it's just, it's determining how strong the structure of the mine is a really important step of safety.
Okay, so our experimentation, we relied on the reaction of calcium carbonate, which is limestone, and then acetic acid, which is used vinegar, and that produces calcium acetate, water, and carbon dioxide. So we relied on the production of that carbon dioxide gas, and we measured the volume of that so that we could measure the purity of the limestone. So if there's like a 50% purity, obviously that limestone is going to be weaker, and it's going to be infiltrated with materials that are going to make that wall less stable. Whereas if you have like a 75% purity or something even greater than that, like 95, which is like the baseline, it will have more structural integrity, which will be like a better spot in the cave for the miners to enter. So our procedure, this is all like, we had to eyeball a lot of our measurements, but we used crushed eggshells. Ideally, you would use around 0.25 grams, and then we reacted it with acetic acid, and then we put a flask, which we also had to make by ourselves with a Sprite bottle, and we submerged it underwater, making sure that there was no gas bubbles in the graduated cylinder beforehand. And then we used this device, which is a tube, and we put the nozzle in here, which would allow the gas from the reaction to enter this bottle. So the displacement of the water would measure how much limestone is in there. And we used Pivner, PV equals nRT, as our equation. And we added all of our data points in there, and that's how we calculated it. So we have a demo of what this actually looked like, because it's a confusing process to, yeah. Okay, so the reaction is in that blue tube right there, and we closed that tube immediately after the vinegar was added, and the water bottle
is slowly filling up with carbon dioxide gas. You're going to see a lot of that water displacing and pushing out, and instead the carbon dioxide entering the water bottle. It will happen soon. It's a process.
It's a little bit slower because we're using vinegar in this reaction, so it's not going to give as much of a bubble as it will with limestone.
Yeah.
Well, you can see it happening there.
Yep, so it's just draining. Okay. And the reason that we used eggshells and acetic acid is because we were thinking, like, if you take a sample of a mine wall and you acid treat it with hydrochloric acid, say for example, then you would get a much larger reaction that would produce carbon dioxide gas. And this was an efficient way to mimic that. So the eggshells kind of represent the sample of the mine, and then the acetic acid would represent the hydrochloric acid that we would use.
Okay, so now for the more technical side of it, you'll see on here we have a little bit of demonstration. This is going to display that the percent concentration of the limestone. Now, how we do this is a little bit of a diagram for what we're using to display it. You're going to notice a lot of these things saying like D4, A, F. All these are the wires that you plug into it, and how you display a number. Let's say you want to display 1. You give power to the A wire and the B wire and the C wire, and it will display 1. And then how you actually go to the next number, if you want to, like, let's say 11 and put it on here, you would actually give positive value to D1 and negative value to D2, which would move you on to the next number. And essentially what it happens is it goes through that process rapidly and what looks like a solid number, but like if you take a camera up to this, you're not going to see a solid number because it flickers so fast. This is the code that we use to do it. It's a little bit simpler because I was able to use a library to speed it up. And then this is the tool that we would use to actually get all these values. It's what we call an ideal gas law tool. The reason we currently don't have it is because it's a decently expensive piece of equipment. Not too much, but a little bit. But what we would do is I would figure out a way of rewiring this into the Arduino board because it sends this information to like a website. So I figure out how to rewire that information into the Arduino board and then use that to calculate the values that we give and then display it here.
Okay, and then our challenges were trying to find a substitute for the mine sample because obviously we can't grab a piece of the mine and use it in the experiment. And then getting the proper materials, we had to 3D print some of our materials that we used during our experiment and find a substitute for a graduated cylinder, which was that soda bottle. And then our time constraints, this is not like the most finished prototype, but if we had more time, we could make it more efficient and permanent. And then figuring out how to wire the ideal gas tool since we didn't have the actual gas tool itself. And then our future steps would be that we would make this into a more portable kit to carry around in the mine so that we could get all the information on each specific type of rock and composition of that rock for the integrity of the mines, and so that later rescue teams could use that in the future. And then questions?
Yes. I believe how we did it is during the problems or during brainstorming ideas. We were all talking through some things, and then I believe you brought up this sort of idea, and then Nico asked if we had all taken AP chemistry, and we sort of said yes. So we all realized that sort of thing, and just that sort of fit in us all taking that class sort of helped step us out to realize that this was going to be a good idea because we all knew the process being taken in hand.
I did an experiment on this, but it was related to eagle eggs and the impact of DDT on eagle eggs. And so the eagle eggs were structurally weaker because of that chemical. And so I was thinking okay, mines can be weaker because there's the different portions of the mine and we can calculate their structural integrity. So I just conducted kind of a similar experiment to that. So any other questions?
Yes.
Yeah, so how much safer do you think his system is compared to current mining practices?
Sure. The current mining practices are really stable. As the pictures before, I showed maps of the limestone mines. The walls there, these giant pillars. The problem is that due to for example, acid rain is a problem in a lot of, or was at least a problem, and we're still facing the effects of it in lots of parts of the U.S. in urban mountain areas like Boulder. And the acid rain can disintegrate limestone quite easily. And over time, if
regulations are like in check, these pillars can get weakened and then just collapse the entire mine.
Let's say that you cannot use the ideal gas equation that you said, PV is equal to MRT. You have a high pressure, a low temperature. How would you adjust your experiment?
So most of the Piston equation is taken on by the Arduino board, but if we were to figure out something like the numbers are too big, there's a couple of things that in code we can do that with. So like we have a rounding effect that we can use to sort of round it to a more positive number for us. And then we can also display it a little bit differently. So if it's a bigger number, instead of displaying two whole numbers in 2 decimal places, we could go like whole numbers or like 4 decimal places to sort of like give that variety if there is a really small number or a really big number.
How do you see this being used in like a mine rescue operation in that like time crunch?
I feel like, if I can take this one, I feel like a big thing about it is like even people in the mines themselves don't know the content of the rock walls, and like they are talking to us about how like they face tough decisions about like not being able to go in and rescue people because the mines are too collapsed. Like in those scenarios, you're already leaving, but they can pull out this piece of technology and see if they actually have enough structural stability to go in and rescue people instead of having to make that decision based off of very little knowledge.
Good job, guys.
Thank you.
Picture.
Thank you.
Which one am I putting up?
Either one.
They're the same.
They're the same.
Okay, good morning, everyone. Thank you so much for coming. This is our prototype thermoshield, and I am Trinity Shears.
I'm Yusuf.
I'm Pacamia.
I'm Philip.
And I'm Sarah. So let's start by going through the problem that ThermoShield is really trying to address. So in the mines, especially when there's a rescue operation going on, there are many hazards like smoke, explosions, fires, and even just the ambient temperature of the mine that make the entire environment very hot and uncomfortable. And when we were speaking with mining experts during rescue operations, the safety of the team that's also rescuing is important. And if they are at risk of heat stroke or heat exhaustion, then it's tougher to actually continue and maybe rescue as many people because you've got to worry about the safety of the team. So by looking at the heat of the mines and by addressing that sort of internal body temperature situation, we're able to make the rescue safer and maybe go longer and actually save more people.
The problem we derived to deepen our research was how can we create a layered PPE system to improve thermal regulation as well as reduce heat stress in mine rescue operations.
To find a solution, we first started off by evaluating the current cooling systems that mine rescuers use. And traditionally, the layers that they wear are 100% cotton, meaning that it absorbs heat and rather than making it away from the wearer's body. So we focused on a product that would meet these 3 constraints. That would expel heat from the body, and that heat would dispel over a cooling layer, and something that would also reflect ambient heat.
The initial focus of our research was to develop a new breathing apparatus that could be smaller, more efficient, but we pivoted to developing a PPE system that is a personal protective equipment system. We first thought of using cotton and polyester, but then they were, while they were affordable, they were also flammable. They were not really efficient at heat management. So we instead pivoted to using hem-tensile base layer, cooling gel core over there, and the reflective flame resistant cell. We prioritized lightweight materials, thermal protection, and mobility when deciding which materials to use for.
So for our outer layer here, we chose to use metallized fabric.
And this is because metallized fabric reflects heat, and for the specific data we used, it has a emissivity score of 0.08, meaning it reflects over 90% of UV, ultraviolet, and near infrared light, which includes heat. So this outer layer will reflect a majority of environmental and ambient radiant heat away from the wearer, allowing the ambient temperature of the mine to not factor in as much to personal temperature.
The purpose of the middle layer, which is this blue part over here, is to dispel that heat into a cooling layer, and it's mainly composed of hydroxypropyl starch, and that is mainly composed of it is chemically derived from potatoes and corn, and this also gives it a environmentally conscious factor as well as affordability due to its mainstream manufacturing process. And we decided to use this because it will strengthen the interaction with water when you add propylene oxide, and this is what gives it its gel consistency.
For our bottom layer, which is the fabric actually touching the rescuer's skin, we decided on a hemp and tensile blend. The hemp itself has a strong cellulose fiber, which is excellent for abrasion and also wear resistance. The thermal regulation comes from the tensile's moisture wicking abilities, and which removes sweats and also promotes evaporative cooling. Put together, they both reduce moisture and also limit bacterial growth, making it lightweight, which improves the breathability and comfortability in the mine, as well as mobility. Since these are both plant-based fabrics, there's also the environmental impact to keep in mind. The tensile is from wood pulp, and then the hemp is from hemp leaves.
Yeah, so putting it all together, we have this layered situation, which makes the entire mining experience more cooled down. So with the captain role, they need to go in first, they stay the longest, they make judgments, so they need to be confident, they need to keep a cool head. So using these types of materials allows the external heat to be reflected, and then the internal heat to be absorbed and moved away from the body. That way the entire experience is more comfortable, and the material itself is more affordable than other options that are there.
Key takeaways: we adapted design based on research under real-world constraints. We improved teamwork and communication throughout this experience. We also learned to evaluate materials and their integrity within our systems. We also practiced iterative design and pivoting, which helped us with which will help us with future design processes.
Thank you guys so much. We will now open it up to questions.
Product could have a outreaching effect to other demographics, other jobs?
I think it is a very versatile fabric. I think there's many blue-collar jobs that have the same environmental factors as underground mining. So construction work, I'd say even police or military outfits will have very similar needs.
What exactly might be the application? Like, I'm sorry, you mentioned the application obviously, but like in terms of the actual piece of fabric, but would it be like a shirt? Would it go on the head? Like,
it would primarily be a base layer, ideally touching the skin to be able to have that moisture wicking ability. I'd say hats could be an integrated platform because the head does produce so much heat, but it could be turned into any piece of clothing.
Yeah, when we were iterating through, we initially thought of the pulse points, where a lot of blood passes through to cool stuff down. So this could be a layer on that stuff, and yeah, we need to do more iteration.
So are you, is this the only thing that they're wearing? Are you putting this on and then you're covering it over something else as well?
We were thinking it can work in conjunction with current protection, because this on its own is durable, so it won't get destroyed, but it's not durable enough to protect them from the mines. So this would work in conjunction with current stuff. The thing is, with cooling, the current stuff doesn't really work as well. Like we said, it's only a base layer. So this with the cooling gel and with the reflective stuff, it could work in conjunction.
Most field engineers would wear the FR. I'm not sure engineer. We have to wear FR for protection. But something you think about is the environmental impact. When you're talking about the environmental impact in your design.
So the environmental impact is brought on in mainly the middle layer and the bottom layer. Since the middle layer is primarily made from starches, it's like a natural compound. It's not necessarily chemically based, as well as the base layer being derived from plants. It's a very sustainable resource, being from wood pulp and again, hemp leaves. The wood pulp I think one of the main current materials is a eucalyptus, a pulp from eucalyptus. So both of the materials are very sustainable and not a non-renewable resource. So you mentioned that it's not particularly durable, so with future iterations of prototype, try to make it more durable, and how do you think you would go about that?
So when we say it's not durable, we mean it's not enough to protect you from like rocks and things. And I mean, there's always a risk of like tears. The main purpose of this is for cooling, not for like material protection. But it is durable enough to function. But when we're iterating further, yeah, we can definitely look at different materials.
Great job. All right, next on up, we're here with Team Orange.
Alright, hi guys, we're Orange Team.
Hi, I'm Chilla.
Hello, I'm Alvin.
I'm Tatiana.
I'm Nate.
And I'm Addie.
This week, we focused on the importance of altering certain tools to assist mine rescue crews and improve their safety through engineering.
To begin, the mine rescue crew is a trained team of specialists that is sent into the mines to rescue the mine workers when some sort of accident or issue occurs. This crew consists of the captain, the gas person, the lab person, the co-captain, the fresh airways, and the medic.
We want the rescue team, as well as mine workers in general, to be able to detect hazards in mines and to take appropriate action. Our problem statement for this project was, how might we improve safety of the mine rescue crew via hazard detection through robotic mechanical technology before they enter the mine?
Our solution to that problem is this, the NATAC drone, which is a sensory drone that can enter the mine with the team.
We had meant, to begin, we wanted to make a robot, but we thought that if it were to accidentally fall over, the technology to make it upright again would be really expensive. Thus, we decided to make it a drone, and it's more mobile and it can be faster than a robot or a human.
So some materials found in the prototype, like excluding electrical parts, we used PLA from a 3D printer, which is plastic, which is fairly cheap. We used adhesives and tape, and I used the Onshape software to design these two parts. This box is actually recycled plastic from a previous student's project, which I think is really cool. Okay, so we faced a bit of challenges. The propeller. So you can see this motor, it's not all the way inside. That's because I used the dial caliper to do the measurements, and so it fits perfectly. So once it gets in there, it's really stuck. And also you can see like this propeller is not real. That is because printing takes time, and we did not have that time.
There was also quite a bit of code that went into this. So the light, basically, as something approaches the sensor here, as Eddie's demonstrating, the light will turn on and flash. Then what the motor code basically tells the motor to do is to rotate it in very small intervals, but very quickly, so it just spins. And not all the code was created by us. We did have some help from Claude and other online resources.
Our electronics consist of many circuit boards, and most importantly, our sensor here, which will detect hazards from 2 centimeters to 20 centimeters away, and the stepper motor that spins our propellers.
Yeah.
Would it be possible to open that?
Yeah. I don't think the green could run. Yeah, so this is basically how the code would work. Unfortunately, we did not have enough wires to actually get this to function. So it would just spin around like that, and thus the propeller would also move. And as you can see, when I put my hand in front of it, the light starts to flicker. And hopefully this will eventually become other technology as well.
This week, we only had time to create a looks-like prototype, so many of the functionalities that would be necessary or preferred for the actual functional hazard detector drone were omitted for time's sake. Something that we would add if we were designing this further would be a multi-gas detector that would be attached to the drone. This would have an advantage over standard gas detection that a person does because the drone could fly around all the different corners of the mine shaft and check for hazardous gases, because currently a person has to manually like walk around and go to all the sides of the mine shaft.
Okay, so if we were to manufacture the drone, we would replace the PLA filament with carbon fibers so that it's lightweight and durable. And if we were to replace the supersonic sensor, we would use a LiDAR system.
And to improve communication, because the light can be easily missed, we will use either the system that the mine already has, aka the leaky feeder system, or we will use a through the earth signaling, which is a low frequency wave that can penetrate through rock and can send signals much easier.
Okay, so this project taught me a lot about working with a team. Each one of us has our own specific strengths, and I thought it was really cool that we could all come together and then apply those strengths to make something that none of us could make on our own.
I think it's really cool that that multiple sources can say different things, but they can lead to different results based on which one works best. And also, I had to really let go of not being able to get everything to work.
I learned about the importance of advocating for your own opinion and taking a step back when necessary so that you can compromise for the greater advancement of the team.
Personally, I learned to not take shame to asking questions or giving ideas, even though they might seem dumb, and that we're all learning at the end of the day, so it's important to ask.
Understanding the impact of mining helped me grow as a problem solver, especially when it came to finding solutions that apply to real world situations.
Thank you so much. Any questions?
One, how would the colors, is there a chance that they might like?
So because this is a prototype we didn't have, and we knew we could only do one, we didn't really concern ourselves with that one too much. But in a final design, we would definitely concern ourselves about that.
And two, for the gas detection, I mean, you mentioned how easy because it's air, but I don't really know much about aerodynamics, but like, would the fact that it's propulsing itself, right, would that disperse the gas too much, or like, do you think that'd be a problem?
I think we would need to do further research on it, and we would probably make like something to like one of the previous groups, like just to go up and down as well.
Yeah, and also I was thinking that maybe the spinning parts that propel the drone could potentially be smaller and maybe displace less air, or maybe have sensors that somehow extend farther out so that before the air that is being propelled by the propellers gets to the gas and has a chance to disperse it, it could detect where it is.
Would this be controlled autonomously out from the outside of the mine?
Yes, because we will basically using a LiDAR detector, which is already in use in things like self-driving cars. So we believe that as this technology advances, it too will be able to control this autonomously.
Do you think there would be any like issues with like trains being that big? I'm concerned it would be like diving deep into the ocean, like the actual being able to transfer rapidly into it.
So we're hopefully going to use like a through the earth signaling, which is a low frequency type of wave that would be able to penetrate through rock to hopefully alleviate that issue.
What was something you learned this week during the illustrations that you use to design the design?
I can do it. Something that really jump-started my thinking for this project was when we went into the mines, I found out that when miners are investigating if there's any hazards in an area that they're about to approach, they send 2 people in there and they just investigate it themselves. And I thought that that held a lot of potential for risk and loss of life. So that was something that really helped with this project.
Oh, and also definitely exploring the Arduinos. Me and Alvin, we were really struggling on it, and that's why we took like many attempts to even get the LEDs to work, and also we had to double check a lot because I kind of put the LED in the wrong way too. Yeah.
Oh yeah.
What was the thought process behind using like a 5-copter design instead of like something like 4-copter? Because I know with 2 it's really hard to scale on like this axis. So I just wanted like was wondering how you steer in that kind of.
Again, it was more like material constraints. We did not have a lot of materials, so 2 was less materials.
We have time for one more question.
Go ahead.
How much would each one cost?
Carbon fiber is approximately $10 to $100 per kilo, and I doubt that one would weigh over 1 kilo. The most expensive part would definitely be the LiDAR. When I was researching the autonomous, like the ones they use for cars are approximately $1,000. That would be definitely the biggest cost of this system.
That's all the questions we
Next we have Team Red.
Good evening, everyone. We're the red team. My name is Aiden.
My name's Hannah.
My name's Bennett.
My name is Rudra. My name is Chris. And we're presenting Pulse, the portable underground life site and signaling equipment. Now, for a problem statement, our question was how might we simplify constant communication and tracking of the rescue team's help and hazard space between the team members, as well as professional breaks. In our research, we saw that one of the biggest issues that mine rescue faced was basically communication between both bases. So we tried to implement a concept of communication more easily.
So just going into that problem a little bit further, during mine rescues, there's a lot of stress going on as it is a difficult event to face. And so that leads to needing a simpler system for communication. So also with the fresh air bases, it can take a lot of unnecessary time and resources to be able to check in with the miners and the people who are on the rescue team. Also, the people on the rescue team are always preoccupied with different tasks, and there can be loud sounds from explosions or any falling rocks or anything that can make communication that's like a normal system a little bit more difficult. And additionally, low visibility, especially if debris are coming in or heavy gases, can lead to issues with finding your teammates.
So there's three basic components to this. The first one is the actual part that the breadboard and its container attaches to, which you have these flexible rubber straps here. And the difficulty with that was it was kind of hard to glue them, which is hence why the prototype demands duct tape. And then you have a 3D printed container here for the breadboard. And ideally, this would be a bit less clunky in the final, but it serves the basic functions. So You're probably not going to be able to see it since the LEDs are tiny, but there are 4 buttons in here, and they all serve different functions and alerts. So the first one here is kind of stand-in for what we would have, which would be a pulse monitor, which is the namesake obviously, and if you can see, it flashes sort of like that. And it could just alert if there's like a health issue quicker than anyone can notice really. And then the yellow one right there is for extreme temperatures. And there's a little temperature sensor, and we couldn't quite get all the coding for that done with the extreme temperatures and with like the room temperature, and since it's not like actually connected to the body, it's a bit off. And then there's this blue one for unsafe terrain alerts, and this green one for gaseous hazards. And the ideal with this is that you would be able to press the buttons and everyone would have a wristband and be able to look down and see which like hazard you're trying to alert.
If we were to make another iteration of the design, there are 5 things we would be doing. First, as Bennett was mentioning about the infrared, about the heart pulse sensor, we would add an infrared sensor to the actual design, so it can accurately track your heart rate and see if you're in danger or unsafe heart rate. We would, as you can see, the thermal sensor is not quite in the correct location. We'd probably put it towards the core of your body where it's more accurate of a reading. We would also have like some radio module. So how we thought communications would work is, since there's a hard line, the hard line would connect to a hub, and then that hub can use radio waves to communicate with all the other mine rescue operation members. As you can see here, it's quite bulky because of the breadboard, microcontroller, and all the wires. So we would have a smaller microcontroller. We would solder most of the stuff. And adding on to that, we would want this to be inside the suit because we wouldn't want this to be a very big distraction that's distracting you from like stuff you have to focus on. It's supposed to be like a side thing you can see, so you know what's happening.
So as far as areas that we have grown by doing this project, we've definitely increased just the communication skills between our team, as we've only known each other for around 6 days, and we've been working on this for even less time than that. So making sure that everyone knows what we're working on, what we're communicating on is very important. And persevering was a big thing with all the circuitry and coding, as we had many compiling issues, many times where wires were accidentally moved. So making sure that we just kept on working and reiterating on our design. And that also helped us to improve our skills in wiring all these peripherals, like these thermal sensors and these LEDs we learned over this course of the week, and also learning how to code in the Arduino C++. And also modeling this to making sure all the dimensions fit, especially with 3D printing this box. We use CAD softwares online, such as Onshape. And with that Onshape file, we were able to slice it and 3D print it, which is very nice for engineering skills. So thank you. We're going to open the floor for any questions.
It sounds like you guys were adding like a lot of sensors to it. Do you think there's like a weight aspect that might be like a little bit like hard to like transportation or something?
Yeah, so with the current aspects, it is a bit clunky, but we don't plan to use this giant. We plan to use a tinier microcontroller, such as like a ESP32, and the breadboard is here for simple wiring. But once we get the schematic done, we can definitely solder all the components together to have a smaller profile. And the thermal sensor and the infrared sensor should be pretty small, because you ever have an Apple Watch, it's not that heavy, right? They use infrared sensors to look into your blood. It's kind of complicated for me, but
there's a whole word for it.
Yeah, there's a whole word for it. But yeah, I don't think weight should be an issue, and it's going to be integrated into the suit that these rescue miners would wear into these caves to make sure that it sits well and isn't hindering their activity.
You mentioned the blue light like represents unsafe terrain. What would you guys would classify as unsafe terrain, or how would it like detect unsafe terrain?
So that's more up to the actual.
It's up to the miner's
Yeah, up to the
discretion for
miners.
that one, because I mean, one of the main points of this is like communication between miners when it's hard to like use verbal methods and also hard to see. But I mean, you can see a light even if it's like foggy or dark. And unsafe terrain, that could be something like floods or like a flood or collapse or something likely like that's happened. So it's really just up to their discretion.
So have you considered how would you make this more accessible to someone who's colorblind?
So a few other like things we were looking at and that we didn't have time were one of the clock displays or the LCD screen. We use LEDs for now since it's much simpler to prototype with, but the LCD screen was another thing that you could use to have more information as well displayed.
Also, we just thought about sound as an option too, if really needed.
The other ideal there is that like they would be able to memorize the order of the LEDs because it's just 4, but I would imagine it might be hard to see the different lighting between a couple of them. So that's definitely something we'll have to improve on in future iterations.
SUMMET?
How did you guys come up with the name?
Well, it's a portable underground light sign signaling and equipment, man. That's what it is, right? And yeah, but like the lights were pulsing and it measures your pulse. It fits pretty well, I think.
So it measures your heart rate. How would you know, because it actually going to relay that information to everyone, but how do you know who is the one that has like the high heart rate or dangerous heart rate?
Yeah, that would have to be iterated on the future, and the whole point of that would be for each probably module would have its interval. Sorry, each module would have its own unique identifier ID, whether that be software or physically, and then the fresh air base could detect an abnormal pulse or maybe the temperature is rising too quickly. They need to send a replacement in, right? So that way you don't have to keep on constantly checking in with that person verbally, like, hey, are you still good? We can just tell by their pulse or their temperature they may need some assistance, right?
Yeah, so like, they might have like 5 separate things for each person that could tell what is currently happening with them and if they're okay in the current situation.
You mentioned the Apple Watch earlier briefly, and it uses some of the similar sensors. So what do you think would set your product apart and should prevent a company like Apple from just repurposing their wearable to like kind of for the same purpose?
So, I mean, patents, but making it robust and making it more suited to the specific miner's condition, because it's meant to be embedded into a rescue suit, whether that be for miners or general rescue missions from all like different departments, right? Like even firefighters going into buildings or something like that. But it's definitely meant to be integrated into the suit and work with other subsystems that they already use, like the hardline hubs and the communication via the leak feeder systems and stuff like that.
Which I guess the way that Apple software works, it isn't very customizable because they're very locked down. So there's a bit more freedom to how we actually implement the software for this.
So those are all the questions that we have. Let's give them a round of applause. Good job.
Thank you.
Hi everybody, we are Team Violet. We chose our summer project to be a mine rescue robot. I am Ev, I'm from Fort Collins, Colorado, and I'm interested in studying chemical engineering.
I'm Kaylee, I'm from Fort Collins, Colorado, and I'm interested in either aerospace or chemical engineering.
My name is Victoria, I'm from Tulsa, Oklahoma, and I'm interested in electrical engineering.
My name's Seth, I'm just from here, Bolden, and I'm interested in civil engineering.
My name's Abdul, I'm from Denver, and I'm interested in aerospace and robotics.
All right. So our key question from which we designed our project is how might we address the issue of locating injured miners without risking additional lives? We were given the general topic that we were looking into improving mine rescue. And so by going to the mines pictured below the words, we were able to come up with and refine questions that we already had.
So through our process, we first researched, took our mine visit, produced our ideas, and prototyped our robot. So a few ideas we had was creating a gas detection device and having the robot be able to transport oxygen to the injured miners and attach different supplies to the robot depending on the adaptability of the mine. About our prototype that we have here, it is a hard body robot with a flexible back that can move depending on the floor of the mine and the rocks. And then we have 4 legs. We wanted to design it to be like a hydraulic, but we weren't able to do that. So it's more like a car suspension, but we have wires here that it can bend and flex depending on what kind of surface it is going over, whether that be like a big rock or just flat.
So over here we have a simplified version of our CAD seat. It's just a simple diagram, but we'll have a hinge that allows it to move. If you can see here, you can see the bottom. It's kind of messy, but you can see the system. And so by using a rope, we can change how it looks, right? By allowing for this rope to be slack, it can just rest perfectly horizontally. But if we add tension to the rope, it'll bend, making it have a shorter body and so on and so forth.
So we're using suspension system. So we use springs for uneven terrain and wheels for movement and equipment constraints.
Yeah, so one of those equipment restraints is we didn't have springs, which if you know about car suspension, you'll know that there are springs involved. So what we did was we took a metal wire that we had available to us and we coiled it around the pipe in order to form a spring-like structure. Since we didn't have enough time or equipment to build that, we also made look-alike prototypes for the rest of it. But we do have one instance where it does work.
And then we also use an Arduino to control our robot. So you have different flashing lights that go on and off, and we were thinking this would control the gas sensor, which would tell you if there's any dangerous chemicals in the atmosphere. And this would allow the robot to move automatically with the different sensors and devices with the Arduino.
So like any other engineering problem, we had some problems. Like first of all, there wasn't a lot of supplies that we could use, like no hinges, which would have been pretty good. No springs, like Victoria elaborated on. Motors are too weak for the string design that would allow this to change its body shape. But like any other engineer, we had to make do and came up with some solutions, which may or may not be great. But anyways, for in place of the hinges, we have fabric and screws, which work well enough, but still allow this to the body to move around and become misaligned. So the problem. And like we said, we use metal wire to make springs. And as for the string that controls the body, we designed this to be manual. But if we had a motor, it could be motorized. So anyways, all this is just to say that our product is not perfect. It's a crude imitation, pretty crude one, but we have the idea here, and it's the idea that we're going for that really matters.
And then further ideas that we have that we would implement and put into our actual robot, a gas detection sensor, which can be the Arduino and another motor can be utilized with lights, a 360-degree camera so that people on the team of the mine rescue, such as the gas person or the map person, can see what they are going up against when they're entering the mine, and then also beacons to guide rescue teams. And then we were thinking about implementing quantum mechanic technology to pinpoint location, which is something we learned about in our sessions here during this week, which can be used through phones and electronic signals to pinpoint locations of injured miners and then also where the robot is located.
And then we created a final mock-up of what we would like our robot to look like in the future. So you can see on the top, there's different attachments where you're able to connect what you would like to see on the robot depending on the mine. There's the hydraulic wheels to allow for the rough terrain, and then the sensors controlling and telling you about the dangerous atmospheric conditions.
And then things we have learned this week, for mine and mine rescue, we've learned about the different team roles, including captain, co-captain, map and gas person, fresh air base, and medic. We've also learned about the limitations of mine rescue, including communication and navigation systems, and then the current resources, which are also limitations, and then the technology we have available. And along with the ventilation systems, including such as the compressed air, which can also serve as a warning, and then emergency response planning and training, which they do in and out of the mine.
And on the other side, on the engineering, coding, and design process, we learned how to use the Arduino code and how to create our circuits. We use the hydraulic design and the hinge mechanics to be able to have our robot function on the rough terrain. And we use 3D design and to create different parts of our robot. And then we overall learned how to manage as a team and work together in all of our strengths. Thank you.
Make sure it's a good one.
So my question for you is that you made a really flexible robot. So like, how would you increase the structural stability of it for like falling rocks and hazards to make sure it won't like fall apart after like falling rock or those sorts of things?
All right. Like Seb mentioned, we have these strings here to control the robot. Ideally, they would be a lot more strong in their design so that the robot wouldn't, break like it might. There'd also be more segments and they'd be shorter so that the robot wouldn't be as long and it'd be more structurally sound. Anything you want to add, Seb?
I mean, it's already pretty tough. Like, if there's rocks that can like smash this like robot made out of wood and all of this stuff, then like you probably wouldn't want to waste your time going in further, right? It's already clear that that section of the mine is like dangerous. So, yeah.
Yeah, and one reason we have the robot is so that if a rock does fall, it would land on the robot and not on the mine rescue team and would not injure and kill further people.
Thank you. Thank you.
Go down, go forward. Reason that makes sense.
Imagine trying to pursue your dream of becoming a miner just to know that for every mine rescue accident, the average death toll is 6 to 7 people. This is the exact problem that we're trying to solve through the Citadel. Good afternoon. My name is Shivam.
My name is Jose Vasquez.
My name is Asher Larry.
My name is Sophia Turpak.
Assignment overview. So during our time here, we were tasked with identifying a key challenge that would focus around mine rescue operations and developing a solution aimed at improving emergency responses, rescuer safety, and victim recovery during mining incidents. During this process, we thought about different things such as what does the problem affect, who does the problem affect, why does it even happen, and most importantly, what needs to be done about it. So during our visit to the Edgar mine, we asked the miner that was giving us a tour a question, and that question is, what is your biggest challenge in mine rescue? In which he said that necessary survival supplies to prolong possible rescue time is a big challenge. And with that feedback, we came up with our final problem statement, which is how might we improve access to necessities for trapped miners while they wait for rescue?
After talking to miners and learning about some of their biggest problems, we came up with some of these alternative original ideas. Our first idea was the oxygen robot, a robot that was small, designed to transport oxygen from the surface to miners that were trapped because of a mine collapse or a landslide, so that we can prolong their rescue time. Another alternative idea was a location beacon, where mine rescuers can place beacons along their route to improve navigation, visibility, and to pinpoint the exact location of where the miners they're trying to rescue are actually located. And the third idea was waste to oxygen. This was a bio-inspired idea that was meant to convert mining waste deep underground into oxygen using a device. However, we decided to scrap all of these ideas due to different problems like feasibility, cost, or just efficiency to solve our primary problem.
And that brings us to our actual prototype. This is the Citadel. It is a safety box made out of steel. It has a sensor and alarm components specifically to help create a location device for when there are trapped miners. So inside the Citadel, there are a bunch of the necessary items. There is the flashlight, there's a med kit, there's emergency gloves, safety hats, water, which is very important because you can get stuff in your eyes or inhale something. And then the most important aspect is the rebreathers. These are typically items that cost around $50 to $100 to supply, and they allow for miners to rebreathe air they've already exhaled, allowing for them to have more oxygen for a longer time when there's a cave-in. The way this works is similar to a fire alarm. This right here would have a sensor, you can see down here with the green light. Preferably, it will be yellow because they use red and green lights in the mine already. That will line the edges of the box so that when you pull the alarm, they start to flash using an Arduino.
Inspired by our workshop here at Summit, we learned how to use Arduinos to create alarms just like these. We use a combination of jumper cables and LEDs to use orange-colored lights, which based on our research is the best color with the wavelength for miners to locate the box. This was a problem that a miner actually identified, and we tried to solve it using our Arduino.
So how this would look like in the mines, where when we visited the mine, we noticed that the mine is divided into many like tunnels and rooms, and so we decided to use that to our advantage and put a little box like one like this inside the walls, like in every single room, so that when there's a collapse in a specific area, they can pull the sensor and it will trigger an alarm notifying exactly where the collapse has happened or like where the emergency is taking place. And this allows for the miners to have quick access to the supplies they need. And this box is going to be about 3 feet tall, 2.5 feet wide, and 1.5 feet deep, so that it can fit all the necessary supplies. And then for our growth, we learned a lot through this project. For example, like all the different roles that the mine rescue team actually has to follow, like the captain, co-captain, medic, etc., etc. And we also learned that there's still so much area for improvement in safety, hence why we were tasked with deciding like a project. So we chose the Citadel to provide quick access to necessities. And we also learned how to collaborate and work together to come up with a good design. And we also learned technical techniques such as how to use an Arduino, which I had never done before, and how to code.
These are our sources. Thank you, everyone.
Now on to questions. One in the back.
So, what trade-offs did your team have to decide between cost, safety, and performance when working on this project?
I can take this one. So one of the main trade-offs is specifically cost. Most of the materials it takes to build those kind of things are either very expensive or in stages where they cannot be utilized yet. The reason why we went with the Citadel in the first place is because it's taking items that we already know exist and implementing them all into one big convenient box of safety.
I'm sorry, I can't hear you.
You mentioned that your product is going to be large, right? So will that limit the accessibility of the micro team? Are you all planning on making sure?
So these are actually going to be stored inside the wall. They will not be boxes on the floor. They will be dug out into holes. The dimensions work sort of flip. They're supposed to be 3 feet wide so that they can fit the rebreathers, but otherwise they are relatively compact. When you think about height reasons as well. So they're low enough to the ground so you can lift it up still. And then it shouldn't impact any kind of rescue because they're there in the wall.
To add on to that, the box is made so that it's extremely customizable. We based our design off of our tour of the Edgar mine and based on what we saw, but different mines are going to need different safety supplies inside their box. They're going to require different things, and that's exactly where the personalization, customization, and adjustments of our box can come into play.
You mentioned that there will be multiple of these boxes in one mine. However, what would you do to make maintenance of these boxes a lot easier? Because eventually the water will have like some things in it that needs to be replaced, or like the steel box might have been corroded in some way. So how would you go that like easily?
I think that like a way we could make sure that the items, especially like inside the box, aren't getting destroyed or anything, is we do like monthly checkups on the boxes. And I mean, the material is made out of steel, and yes, it could corrode, but steel is like relatively stable. So there shouldn't be like too many problems. And considering these sit inside the walls, I don't think there will be like too much problems with like water leakage.
I'm curious, and for you to answer this, about like why you're positioning it on the entrances to the mine, because it seems like a lot of scenarios where this equipment would be needed would be better placed on like the sensor. Because like during like the event of a cave-in, for example, you wouldn't really be able to see the lights. Or if there's a trapped person, by finding one of these boxes, you've also already got the exit. So like at that point, there's not a need for the inside.
So when we say entrance, we don't mean like primary entrance. We mean entrances to even like the smaller little caves. You could go back a few slides. Yeah. So if you take a look right here, we're kind of more thinking that they're in primary areas. The only reason we specified entrances is because those are the most well-known areas. They're not entrances closest to the exit. And as we saw, some of the entrances are dead ends. So at least having that ability to see where the primary location is to send a rescue team down is the most important part.
That's all the time we have for today.
You want to leave the box open? Yeah, leave it open. Leave it open.
Keep your prototypes up there. It would be great for everybody to have their prototypes up there. All of the same.
Bring it up. Wait, where's the second half of it? Thank you so much.
Yeah.
I don't know.
It looks like it's
No way.
Somewhere in the
What am I supposed to do? I don't know, look over the camera. Look at Jenny's camera.
Let's look to the middle. Oh, look at the actual picture.
Oh, yeah.
Hell yeah.
Remove that.
Oh yeah, Nico's told.
All right, 3, 2, 1.
Cheese.
Malaga.